Ever stop to think about how, well, anything gets made anymore? Or how a roller coaster knows exactly when to drop? There's this invisible intelligence running pretty much everything behind the scenes. And today, we're going to pull back the curtain on this unsung hero of our modern world, the PLC.
So here's the game plan. First, we'll nail down what a PLC actually is. Then, we're going to peek inside its head and see how it thinks. We'll get into its programming language, which is super cool, and even touch on some of its more advanced tricks, like something called PID control. And finally, we'll connect all the dots to the world around you.
I mean, just look at this. The scale of it all is kind of mind-boggling, right? Every single step, whether it's putting a bottle cap on or assembling a car door, needs to be perfectly timed, totally reliable, and incredibly fast. Now, what's making all that happen? It's definitely not a person with a clipboard and a stopwatch. It's something way, way cooler.
And that brings us right to the main event, the star of our show, the Programmable Logic Controller, or as everyone calls it, the PLC.
Okay, so at its heart, a PLC is a computer, but it's a very, very specific kind of computer. It's not built to surf the web or edit photos, nope. Its entire reason for existing is to listen to sensors, read button presses, and then, based on a program we write, tell motors what to do, open valves, and just generally run the show. And here it is. I know, it's not much to look at, is it? But this little gray box, this unassuming thing, is the brain behind those gigantic factory floors we just saw. All of that complex, powerful machinery is being directed by one of these.
And this picture really hits home what makes them so special. Your laptop would last about 5 seconds on a factory floor. It's hot, it's vibrating, there's electrical noise everywhere. It's a nightmare for normal electronics. But a PLC? It's built like a tank. It's designed for that chaos. It's the ultimate bridge between our clean digital code and the messy, powerful physical world of industry.
So how does this industrial strength brain actually, think? It all boils down to a super simple, super fast process called the scan cycle.
Unlike your computer, which is juggling a million things at once, a PLC has a one-track mind, in the best way possible. It just runs this 4-step loop, over and over and over again, so fast you can't even see it. Step 1, it checks all the inputs. Is that button pushed? Is the sensor on? Step 2, it zips through the program you wrote. Step 3, it turns the outputs on or off based on that program. And step 4, a little bit of internal cleanup. Check, think, act, repeat. That's it. Thousands of times a second.
Okay, so if we want to tell this PLC what to do, we need to speak its language. And the most common, the most foundational language out there is this really intuitive visual thing called ladder logic. Now, to get why this looks the way it does, you gotta go back in time. Before PLCs, factories used these massive cabinets filled with clicking electrical relays and miles of wire. The genius of ladder logic is that it was designed to look just like the wiring diagrams for those old systems. This made it super easy for the electricians and technicians who were already on the factory floor to understand it. It just made sense to them. And it really breaks down to 2 basic building blocks. You've got contacts, which represent your inputs, things like buttons and sensors, and then you've got coils, which are your outputs, motors, lights, you name it. Really, just think of it like this. Contacts ask the questions, and coils are the answers. And this is how we build a simple sentence in that language. You see how we have 2 inputs, A and B, one right after the other? That creates what's called an AND condition. For power to get from the left side to the right and turn on that output, X, you need input A and input B to be active. If just one of them is off, nothing happens. If you're more of a numbers person, this truth table shows the exact same logic. You can see it right there in black and white. The only, and I mean only, way to get a 1 or an on for that output is if both A and B are also 1. This super simple idea is the foundation for almost every automated process you can imagine. But let's be real, not everything in the world is just on or off, is it? A lot of processes need a delicate touch. They need a dimmer switch, not a light switch. For that, we need to dive into one of the most powerful tools a PLC has, PID control. Exactly. Think about it. You can't just blast a heater at full power if you need to keep a tank at exactly 95.3 degrees. You'd fly right past your target. You need something smarter, something that can make tiny, constant adjustments. You need a feedback loop, and that's where PID, that's proportional, integral, and derivative, comes into play. All right, first up is P for proportional. This is the gut reaction.
It looks at how far off you are from your target right now and reacts in proportion. So if you're really far from your target temperature, it cranks the heat. If you're getting close, it eases up. It's the right now part of the equation.
Next is I for integral. Think of this as the system's memory. It looks at the error over time. So let's say your system is always just a tiny bit too cold. The proportional part might not care that much, but the integral part will notice this nagging, persistent error and will slowly, gradually add a little more power to get rid of it for good. And finally, there's D for derivative. This is the crystal ball. It looks at how fast things are changing. So if the temperature is screaming towards your target, the derivative part can predict, whoa, we're going to overshoot this thing. And it starts to cut the power before you even get there. It prevents those wild swings back and forth. Now, if you're sitting there thinking, man, this sounds a whole lot like calculus, well, you're absolutely right. And the source material had this fantastic warning about it, which I just love. The math behind this stuff can get pretty hairy. But, and this is the beautiful part, the PLC does all that heavy lifting for you. You don't have to solve these crazy equations. Your job is to tune it. You just adjust the P, I, and D values, tweaking how strongly the system reacts, how much it remembers, and how far it predicts until you get this perfectly smooth, stable performance.
Okay, let's zoom back out for a second and put a bow on all of this. What's the big picture here?
So what's the big takeaway here? At the end of the day, a PLC is just a super tough computer built for one job. It thinks in a crazy fast loop. We can talk to it using a visual language that makes sense, and it's powerful enough to handle not just on-off stuff, but delicate processes too. But really, the most important thing to remember is that these little brains are everywhere, silently making our world work.
So the next time you go through an automatic car wash, or you're on an escalator, or you just see a traffic light change, stop and think for a second. You might not be able to see it, but now you know about the hidden brain that's almost certainly running the show. Now that you know the basics of their language, how differently will you see the world around you?